What is dog times tree? This is a pretty nonsensical expression at first glance, but I promise that if you just stick with me, I will explain what lessons we can learn from it and why we should care about questions like this. Here is a brief overview of what to expect in the video. First, we will explain what a unit is and how to do basic arithmetic with them. I will note that throughout this video, I will use the terms unit and dimension interchangeably. We will briefly explain this choice of vocabulary later. If this is already comfortable for you, you are welcome to skip to the next part. Once that is established, we will explain what conversion factors are. At this point, we will have laid out the foundations of what units are and what we can do with them. Beyond that, we will take a look at how we can solve problems using these ideas. Then we can talk a bit more abstractly about some of the more interesting ideas that result from this kind of analysis. And last but not least, we will cover the exceptions, the fine print, where we explain special cases, such as units with weird properties, or how we can define our units in all sorts of non-standard ways. You may walk away with some interesting and creative ways to understand the world from the lens of dimensional analysis. Let's start by talking about what a unit is. A unit represents some kind of quantity. For example, a meter, a kilogram, a second, an apple, or a dollar. However, we generally do not consider numbers to have units. For instance, the number 1 is considered unitless, as is the number 2, or 12, or negative 5.3. This is because the number itself doesn't really tell us what quantity it's describing. We don't know if it's describing an apple, a length measurement, or a view count of this video. Now let's talk about the arithmetic we can do with these units. I can take any unit and multiply it by a dimensionless value. It should also be fairly intuitive how to add and subtract these units. It is as if we are treating the unit like a variable. In fact, sometimes we can even add different units together. For instance, 30 seconds plus 1 minute is still a coherent quantity, as both of these units measure time. When different units can be added together, we call these commensurable units. However, this isn't always the case. 3 meters plus 20 seconds is nonsense and cannot be combined, in the same way that 3x plus 20y cannot be simplified. These units would be called incommensurable, because one measures length while the other measures time. How do we describe speed? If my car travels 100 kilometers in 2 hours, we divide these values to get that the speed is 50 kilometers per hour. The word per literally means divide. We might not be able to add these incommensurable units together, but we sure can divide them. A division of units is simply describing a ratio of those units. Since anything can make a ratio with anything else, we can divide all kinds of units. Mass divided by volume gives density, and amount of money divided by a number of apples would give you the price of an apple. But what about multiplying units? We could obviously just multiply both sides of this equation by 2 hours, and then we would have time multiplied by speed to get distance. So it seems like there are some units we can multiply together. Let's look at some more examples. Here is a meter. Here is a meter times a meter, also known as a square meter. We can use this square meter as the basis of our area measurement. A cubic meter can be used to describe volume. This is also part of the reason why units are also called dimensions. The description focuses on the exponent of the unit more than the base unit itself, but it is still describing the same thing. We can always multiply units in general. When multiplying units, we are pairing each of the first units with each of the second units. Here are a few ways to visualize how these quantities are related. You are always allowed to multiply units in this way. So now we have learned that we can arbitrarily multiply and divide units together. But whether or not there is something meaningful or useful that can be described in this way is a different matter. Here is one example. We will multiply the number of students with the number of minutes. This may initially seem like a meaningless unit until you consider the context of calculating the number of problems the students will solve. Assuming that every student solves 1 problem per minute, this multiplication gives you a value that you can use to calculate the total number of problems solved. If we map these units onto a rectangle, you can view the number of students as the length, the number of minutes as the height, and the number of problems solved as the area. So the key takeaway here is that even though we can only add and subtract commensurable units together, we can multiply and divide any units together, even if they are incommensurable. What even is the product or ratio of units then? We don't have to imagine this as radically changing the identity of a unit, combining two units to get a completely different thing. All it is simply quantifying something formed by other quantities, describing how the numbers are related. Now that we have established this, notice that units can be inserted into expressions just like any value or variable, and the standard rules of algebra apply to them as if they were just variables. Some units we have to just start with. These are called base units. Once you have a set of base units, you can then create other units by combining those base units using multiplication and division, which are called derived units. What is considered base units depends on the context of the problem. With scientific empirical measurements, the SI standard units here are typically what we consider to be base units. However, plenty of other things can be base units too, like apples, people, or dollars. So let's say I have a unit, and I would like to convert it into another unit. For example, how many centimeters are in 12 meters? Most people would simply multiply by 100 here. However, this isn't rigorous without the units. If we try to include our units, we have a little bit of a problem. Without arbitrarily swapping out units, how would this work? We know that 1 meter is equal to 100 centimeters. Let's now divide both sides by 1 meter. As you can see, we are not dividing by 1, we are dividing by meter. Look how even though the right side has a bunch of units, the left side is a dimensionless one. Now let's go back to our 12 meters. We know that multiplying any expression by 1 doesn't change its value, so let's multiply this by 1. Since 1 is equal to this expression we found earlier, we can substitute it. Now, if we cancel our units, we properly obtain that this expression is equal to 1,200 centimeters. This expression that we found is called a conversion factor. Conversion factors, by definition, must be equal to a dimensionless 1, and they convert the unit in the denominator to the unit in the numerator by simply multiplying itself to the value to be converted. Notice that if we just take the reciprocal, we get the conversion in the other direction. It is easy to convert commensurable units, like from seconds to minutes, or from meters to kilometers, or from dollars to euros. However, to convert incommensurable units is a little bit more nuanced. On one hand, there is no way to convert apples to dollars, because one measures economic value and the other, well, measures apples. However, you can make it work by making additional assumptions. For example, let's say 10 apples equals $3. Normally, this kind of equality is a bit nonsensical, but if you treat each unit solely in terms of its economic value and assume that each apple has the same value, then you could justify this equation, which allows you to find your conversion factor, which then allows you to convert these units. For situations like this, context matters a lot. Later in this video, we will see some practical applications of this kind of conversion. Alright, we have spent this entire time laying out some basic terminology and the arithmetic properties. Let's now look at some example problems. 10 blats equals 1 blet. 1 blet equals 3 blits. 10 blots equals 9 blits. 2 blots equals 15 bluts. How many bluts is 22 blats? Obviously, these units are nonsensical. However, keep in mind that sometimes you will get problems in the real world where you may have to convert units that you have never heard of before, whether it's a unit of length or a currency from a foreign country. Let's just pretend that these units are like that. In addition, remember that conversion factors can convert incommensurable units under some contexts, so that would lend more believability to the fact that this type of problem could appear in the real world with some arbitrary values. Firstly, let's write out each of the statements of equality in the problem as equations. Next, realize that we are converting our 22 blats to bluts. In order to do this, we need to make intermediate conversions, from blats to blets to blits to blots to bluts. Next, divide each equation accordingly so that we get our conversion factors. Finally, we multiply our conversion factors together and cancel like factors from the top and bottom. That's it. Notice how much easier the problem is once you incorporate the conversion factors. The conversion factors encourage you to plan your intermediate conversions, but then as each conversion is laid out clearly, the final calculation is done all at once. Let's try this problem next. How many cubic millimeters are in a cubic kilometer? First, we notice that there are 1,000 millimeters in a meter, and there are 1,000 meters in a kilometer. Thus, the answer is 1 million, right? Let's consider that 10 millimeters make up a centimeter. However, it takes far more than 10 square millimeters to form a square centimeter. The fact that the unit has an exponent means that the conversion requires a little bit more work. Let's begin by setting up our conversion factors. Notice that we can combine these two conversion factors to form a single conversion factor that will be easier for us to use. Next, we multiply our conversion factor to our starting value, and notice that it only cancels out one of the units. We have to continue multiplying our conversion factor until all of the units are properly canceled, giving us a final answer of 10 to the 18 cubic millimeters. For reference, that is 1 quintillion, or 1 billion billion. Now consider the following problem. 5 chickens can lay 18 eggs in 3 days. How many days does it take 100 chickens to lay 10,000 eggs? The hidden assumption is that each chicken lays the same amount of eggs per day. In other words, the number of eggs per chicken per day is constant. Here, K is known as the constant of proportionality. Using our constant, solving for the number of days is simple. We just plug and solve. Notice that eggs per chicken per day is the unit we use to help us find the answer. Similarly, we can also understand this unit as its reciprocal, chickens times days per egg. To better understand how this unit works, consider this rectangle, where we represent the number of chickens as the width and the amount of days as the height. Each column represents the amount of eggs a single chicken produces. Each row represents the total amount of eggs laid each day. The total area represents the total number of eggs laid. We can thus write our equation as 5 chickens times 3 days equals 18 eggs. That doesn't seem to make sense. How can we multiply our chicken and day units to obtain eggs? Let's see what's going on here. Suppose we have 1 chicken and 1 day. Does this mean we have 1 egg? Not necessarily. Imagine that this rectangle represents the total work that chickens do, but then that work unit needs to be converted into some amount of eggs. We can treat the K we found earlier as our conversion factor from this work to eggs, and now our units finally line up correctly. By understanding how units and conversion factors work, proportion problems can become much easier to set up and solve. Having a good grasp on dimensional analysis also gives us a way to sanity check our work and ideas. Here, sanity check means a very simple, quick observation to verify that we have made a mistake. Here's an example. Heron's formula is a formula that allows us to determine the area of a triangle knowing only its side lengths. Let's say that I write the formula down from memory like so. How can we use dimensional analysis to quickly demonstrate that I have made an error? Notice that all of these values are lengths. When we multiply under the square root, we get a length to the power of 3. Taking the square root results in a length to a power of 1.5. This is not the formula because area should be length to the power of 2. We are missing a length factor under the square root. The correct formula should be this. Dimensional analysis here may not get us to the right answer, but it certainly told us something was wrong. So now that we understand what units are and how to apply dimensional analysis to solve problems, let's look at some amusing consequences of applying the theory. For starters, let's take a look at percentages. The percent symbol itself can be understood as having 2 properties. First, it is dimensionless. Second, it is the value 1 over 100. Consider an item sold at a store for $20. Let's say there is a sale and it is now 40% off. To obtain the sale price, we multiply the original price with a value 60%. Since the unit of the sale price is the same as the original price, we know that the 60% value has to be dimensionless, because otherwise the unit would be different. If we treat the percent value as a constant, replace it with 1 over 100, we can easily simplify to obtain our answer. We can think of the degree symbol similarly. The degree unit is actually a quite unnatural way to define an angle measure. To see why the degree unit is considered unnatural, ask yourself why there are 360 degrees in a full circle. If a full circle was defined as 100 degrees, we simply rescale everything. Right angles are now 25 degrees instead of 90. Everything still works as normal. The number 360 is an arbitrary historical convention that stuck. In fact, there are other units that measure angles such that a full circle is defined differently. For instance, a full circle is 400 grade. The natural way to measure angles is in units called radians. The angle measure in radians is defined as the length of the arc divided by the length of the radius. Not only does this definition not involve any arbitrarily chosen values, when we use angle measures in all sorts of formulas, using any other unit gives us erroneous results. For instance, to compute sine of an angle, we can use this infinite polynomial, known as its Taylor series. If we plug in the radian measure, we get the expected answer. If we plug in the degree measure, the answer is totally wrong. This is why it is so important to write the degree symbol, or at least make it clear that your measurements are in degrees. The degree symbol itself is the conversion factor from degrees to radians, which turns out to be equal to this. And since it is a conversion factor, it is also a dimensionless value. Not only that, the radian unit itself is oftentimes considered to be dimensionless. Remember that we define the radian as the arc length divided by the radius length. Length divided by length cancels, resulting in a dimensionless value. Even the video you're watching right now was programmed using this concept. An even more bizarre consequence is the fact you can coherently measure fuel economy with area. Suppose you have a car that can travel 30 miles per gallon. We could, if we wanted to, take the reciprocal and call it 1/30th gallons per mile. Let's do that. Gallons measure volume and so do cubic meters. This allows us to convert gallons to cubic meters. Miles measure length, so obviously this can be converted to meters as well. Meters cubed divided by meters gives square meters, which is a unit of area. We can now coherently say that this car's fuel economy is 0.0784 millimeters squared, which is approximately the same as 30 miles per gallon. This seems kind of ridiculous, right? But can dimensional analysis reveal something deeper, a way to make this representation intuitive? Let's pretend that as the car is traveling and burning its fuel, it is leaving the volume of fuel it burns behind in the form of a solid tube. It is as if the car is squeezing the fuel out like a tube of toothpaste. The volume of the tube is the volume of the fuel, and the length of the tube is the distance traveled by the car. The volume of a cylinder is the area of the circle times the length of the cylinder. By solving for the fuel economy, volume divided by distance, we get that the area of the cross-section of this tube is the fuel economy we are measuring. The larger the area, the wider the tube. The wider the tube, the more fuel it burns, the less efficient it is. So now we have a preview of the power of dimensional analysis, but it turns out that dimensional analysis is a lot more arbitrary than you may expect. We can make up all kinds of rules for our units. In this way, we can create or use units that have special properties. The imaginary unit I is defined as the square root of -1, which means it has the special property that the unit squared is simply a dimensionless -1. We also mentioned before that radians are dimensionless. This is also not absolutely true. You could arbitrarily decide that the radian unit does have its own unit, such that you cannot just add or subtract it with dimensionless values. If you choose to do this, you would need to modify your equations and expressions accordingly. These modified expressions and equations still work perfectly fine, but they are just more cumbersome to work with, which is why most people just treat them as dimensionless. Plenty of other dimensionless values can arbitrarily be assigned a dimension in a way that is coherent to the problem. You just have to be a bit careful that your selection of definitions is meaningful. One example is the number of permutations of n objects. The formula for this is n factorial, which can be interpreted as a value with n dimensions. There are so many more complex or interesting applications of dimensional analysis, but this should be a good starting point. A lot of the time it's just applying the ideas in a straightforward manner that helps you organize your understanding of what the values in an expression are describing. But occasionally, you get some clever insights or cool ways to select your unit definitions. In those cases, it's all about your choice of standard, what is most useful to you. When are you allowed to break the rules? Basically, whenever and however you want, as long as it is coherent, consistent, and meaningful. Let's go back to where we began, the title of our video. What is dog times tree? We now know that units can be multiplied together arbitrarily, so the answer is simply dog trees. You can use this unit to describe anything you would count that is assigned to each pair of a dog in a tree. Without context, this answer is probably just as silly as the original question, and immensely unsatisfying. And in one sense, that is kind of true. But nonetheless, we are allowed to invent units like this, the same way we can invent any derived units. Dog times tree is probably not a practical use case you will ever see in your lifetime, but knowing how to arbitrarily multiply and divide units and what they mean may help you open up to some new concepts and perspectives that will lead you to some deeper understanding in both math and science. So I apologize if any of you feel underwhelmed, but if you want to see some more actual funniness with units, you could check out Joseph Newton's very funny video on cursed units. This video by Kier and Borovac shows how we can treat the 7 SI units as a vector and some clever things we can do with it as a consequence. In the future, I will be posting more math videos that use more interesting applications of dimensional analysis, so if you're interested in those, please support me by, in addition to subscribing and sharing the video, checking out the sponsor of this video, Brilliant.org. Brilliant.org is a learning platform that's perfect for curious minds like yours. It offers a wide range of interactive lessons in math, as well as data science and computer science that cater to all levels of learners. Whether you're a beginner or an advanced student, they have something for you. Not only that, new content is added every month, so you never run out of things to learn. Brilliant's bite-sized lessons allow you to learn at your own pace, making the journey both enjoyable and effective. For example, the geometry courses offer a lot of fun and interactive puzzles, where you can play around with areas and volumes. The best part is Brilliant is free to try for 30 days, and if you like it, you can use my link brilliant.org/Julie, and the first 200 subscribers will get 20% off a premium subscription. So don't wait, check it out and get learning. Thanks for watching, and I'll see you next time.